So let's work out the Kozelidov Hamiltonian and its consequences. So again, this is a hierarchical triple. We have the binary pair here, M0 and M2. M2 is a massless particle, and there is a perturber, a mass M1, on a distant orbit where R, the separation between M0 and M2, is much, much less than the semi-major axis of the outer binary. We're assuming that the outer binary, M1, is in a circular orbit. And if the outer orbit is circular, and we choose that to be the orientation, so that's the planar reference of zero inclination, the angle psi, which is the angle between R and R1, is given by this expression in terms of the orbital elements. The orbit of the outer is now only present in terms of the mean anomaly, cosine M1 and sine M1 here in these terms. So we want to know the cosine squared. So let's calculate what the cosine squared is. We can write this expression then as A times cosine of M1 plus B sine of M1, where A is this first coefficient, B is the second coefficient. If we then calculate the cosine squared, as it appears in the Hamiltonian, what we have then is, and this is the first place where we do a secular approximation. A secular approximation means that we are only considering the long-term evolution of the system. So this orbiter, M1, around the binary, we can average this out. If we average the motion, we're going to get rid of the dependency on the mean anomaly of the outer binary. So the average of cosine squared psi is going to be then. Now, because the cosine and the sine are periodic function, the linear ones, they cancel out. And the average of cosine square and sine square over a period is equal to half. So if we place this back, then the average of cosine squared then is half of a squared plus b squared. Now that's the average along the orbit of the outer binary. Let's substitute now the expressions for A and B, where we simplified the notation here by defining omega bar as omega plus the true anomaly. So we need the square of these. What we have with them is that we already see that the cross term cancels. So it's already clear the trigonometrical simplifications that are going to happen here. You have here cosine square of omega bar that is multiplying sine square of big omega plus cosine square of big omega. So that leads to 1, the sine square and the cosine square of big omega, and then you end up only with the cosine square of omega bar. And for the other term, the same thing happens. You have sine square omega bar cosine square of the inclination, and the same factor here, sine square omega bar times cosine square of inclination, that is multiplying sine square of omega plus cosine square of omega. So again, that's going to give you 1, and then you end up with a simpler expression. You can substitute now cosine square of omega by 1 minus sine square of omega. Now group the signs. And 1 minus the cosine square of the inclination is the sine square of the inclination. So this simplifies. We have then our final expression for the average of cosine square psi. Averaging the outer orbit means that we're not considering anymore the orbital motion of the mass M1. We are considering that mass to be spread around the whole orbit like a wire. That's the geometrical interpretation of this average. And a very important thing happened here when we did this average, that it happened that the longitude of the ascending node canceled out from the Hamiltonian. So you'll remember again the Delaunay variables in angle action. The Hamiltonian not depending on an angle meant that the action was conserved. Because the longitude of the ascending node canceled out, that means that this system, the inner binary, is conserving the vertical component of the angular momentum. So we found, at least for the averaged problem over the outer orbit, that the vertical component of the angular momentum is constant. Now, because LZ is equal to a combination of the semi-major axis, the eccentricity, and the inclination of the inner binary, the constancy of this quantity implies a correlation between these quantities for the inner binary.